So thermal bimorph principle, not only is it used in thermal sensing in MEMS, but it's also used in thermal actuation. This is actually something that I would say most of us are familiar with in practice, if not in specifics. How many of you guys in your apartment, your home, or whatever have an old school thermostat where you like rotate the dial to set the temperature? That is a thermal bimorph. That is literally what we're talking about today. Bimetallic strips are work on the thermal bimorph principle. Okay. So a thermal bimetallic effect allows temperature variations in microstructures to be exhibited as a displacement of a beam. Okay. So a thermal bimorph consists, let me just write this down. Consists of two materials joined along their longitudinal axis. Serving as a single mechanical element, excuse me. So I'm going to attempt to draw something here. So I'm going to start with one kind of thing on top here. And so this particular material in pink will have its own Young's modulus. This subscript 2 is just because I'm considering this to be material 2. And it will also have its own alpha, where alpha is going to be the coefficient of thermal expansion. Okay. So I'll just make a note over here. Alpha is coefficient of thermal expansion. And it's usually, I believe, given as a percentage change. So you might see it expressed as something like parts per million per degrees Celsius or potentially per degrees Kelvin. So I'm just going to put over here ppm per degree. And I'm just going to use that capital T to represent temperature. So it's just a rate of change per unit's temperature, where that unit might be whatever we need it to be for any given problem. Okay. And then this is going to just sit atop some second material. And so I'm going to try to draw that guy right here. Like so, where our material in gray is going to be material 1. So it has its own specific Young's modulus. It has its own specific coefficient of thermal expansion. And then I'm going to label a couple of dimensions here. So this guy right here is going to be the thickness of material 1. This dimension right here might be the width of material 1. This guy right here might be the length of material 1. And then very similarly, we would have some thickness to width to and length 2, like so. So if these two materials have different coefficients of thermal expansion, each layer will undergo a different change in length for a given change in temperature. Because the materials are considered as tightly joined at the interface, this difference in thermal expansion causes the beam to bend towards the layer with a lower coefficient of thermal expansion. So effectively what we should see would be something like this. So if I'm looking at a side view and I've got my material 1 as, say, a cantilever beam, and I've got my material 2 as a cantilever beam like so, where this guy has coefficient of thermal expansion A2, and this guy has a coefficient of thermal expansion alpha 1, then under some sort of temperature change, we would see some sort of bending like this, potentially, where this will be a rather exaggerated thing. Where this length from here to here, I'm going to call this L2 prime. And we could say that L2 prime, which is the length after heating, would be our nominal length, L2, times a factor of 1 plus alpha 2 times our change in temperature. And very similarly, we would have a length L1 prime here, where L1 prime would be L1 times 1 plus alpha 1 times our change in temperature. And based on the way that our beam is bending, we would know that alpha 1 is actually less than alpha 2 in this particular case, because we'll always bend towards the smaller coefficient of thermal expansion. So effectively, the higher coefficient of thermal expansion means that that beam is going to tend to expand more and push the other one down. Okay. So under a uniform temperature change, of delta T, the beam curves and assumes the shape of a section of an arc of length L. And the radius of curvature of this arc is given by this particular equation, which I'm just giving you a heads up is long and gross. So I'm going to have 1 over r, where r is my radius of curvature, will be equal to, and then I'm going to do the denominator first because it's longer. So we would have the width of material 1 times the Young's modulus for material 1 times the thickness of material 1 squared, that whole quantity squared, plus the width of material 2 times Young's modulus for material 2 times the thickness of material 2 squared, plus twice width of material 1, width of material 2, Young's modulus for material 1, Young's modulus for material 2, thickness of material 1, thickness of material 2, multiplied by twice the thickness of material 1 squared, plus 3 times the thickness of material 1 times the thickness of material 2, plus twice the thickness of material 2 squared. That's our denominator. So large gross expression. Our numerator isn't quite as big and ugly, but it's pretty close. Our numerator is going to look like 6 times the width of material 1, the width of material 2, Young's modulus for material 1, Young's modulus for material 2, thickness of material 1 times thickness of material 2, multiplied by the thickness of material 1 plus the thickness of material 2, multiplied by the coefficient of thermal expansion of material 1 minus the coefficient of thermal expansion for material 2, times finally our change in temperature. So that the radius of curvature is then dependent on not only the geometrical properties of the two different parts of the thermal biomorph, but as well as hopefully, obviously, any change in temperature. And then the angle of the arc, theta, is simply the length divided by the radius of curvature. So I'm going to try to draw a simplified picture here that's going to kind of relate all of these things together, okay? So over here on the left, I'm going to have my anchor, and then this line right here is going to characterize my beam when there is no deflection, okay? Then I'm going to do a line in gray that's going to look at like my, actually, let me scooch this down a smidge because this picture might need it. Sorry. This guy in gray is going to be what my beam looks like after deflection. So I'm going to choose to draw it up like this. And so this distance right here is R. This distance right here is also R because our beam forms an arc length. This angle right here, theta, is the angle of the arc. And then using a little bit of trig, this length right here is our sine theta. And from this, our amount of deflection D is R minus R cosine theta. So these are all of our relationships. And so what I want us to do now is to look at an example problem, kind of trying to tie all of this horrifying stuff together into how do we use it to calculate things. Yes. At least from the textbook that I got. So let's think about this really quickly. So
radius, which is 55.
let me think about it. So when you said as temperature So if delta t were 0, then the radius would be infinitely large, right? And a radius of curvature of infinite length would imply a flat surface. Yeah. And then as our temperature increases, that radius gets smaller and smaller and smaller, so that the bending becomes more and more finite. Yeah, okay, that makes sense. Sorry, I had to think about it for a moment. All right, so what I want us to look at is an example. Wherein we have a bimetallic cantilever beam, but in this case, we are going to have materials having two different lengths, okay? So I'm going to put one material on bottom, and just for the sake of argument, in this particular time, I'm going to call this guy material 2. So it's characterized by some Young's modulus and some coefficient of thermal expansion. And this guy will have some length, L2. And then deposited on top of this guy will be another material, significantly shorter in length, characterized by E1 and alpha 1. Here is our length L1. And this is a side view. And so a top view might be something like, or actually this wouldn't necessarily be a top view, it'd be kind of looking towards the face. So like that. So we would see some thickness T2, width W2, thickness T1, and width W1 like so, where let's say that L1 is 100 microns, L2 is 200 microns, T1 is half a micron, T2 is 1 micron, W1 is 20 microns, and W2 is also 20 microns. Let's say that material 1 is aluminum, which has a Young's modulus of 70 gigapascals. Let me write that better. That looks like shit. And a coefficient of thermal expansion of 25 parts per million per degrees Celsius. Material 2 is silicon nitride, which has a Young's modulus of 250 gigapascals and a coefficient of thermal expansion of 3 parts per million per, excuse me, get that backwards, degrees Celsius. And so we are asked if the beam is straight or flat at room temperature, what will the vertical displacement of the free end of the beam be at a change in temperature of 20 degrees Celsius, and specifically an increase of 20 degrees Celsius. So we'll leave that as a positive quantity. Yes.
Is that a difference in temperature between the two beams or the beams and the environment?
The end of the beam and the environment, because they're both undergoing that same change in temperature.
Right.
So we have effectively some sort of composite beam. The silicon nitride has a significantly lower coefficient of thermal expansion, so we should expect our beam to bend in the direction of the silicon nitride. So I'm going to draw kind of a picture here, and I'm going to flip my beam upside down just so that I can draw the curvature up so that it more or less matches what this diagram is. Okay. So over here on our anchor side, we've got our silicon nitride. I'm just going to try to draw this out fairly straight or so. The dimensions don't particularly matter since we have all of those as a thing. And then I've also got now down here, maybe something like this. Okay. So I can kind of subdivide this thing into different lengths, right? So if I call my anchor A, this is point B, and this is kind of point C, then the reason why I'm subdividing this is because we are only going to see that thermal bimorph curvature along the span from A to B, right? Because that's the only span where we have the two materials that have different coefficients of thermal expansion. Along the length from B to C, we should just see a linear increase in the length of the material because it doesn't have anything expanding at a different rate that's causing it to deflect one way or the other. So from this, generally speaking, our curvature should look something along these lines. So we would have a curvature to, let's say, roughly this point right here. So this is what I'm going to call DB. And then from this point on, it's going to be completely straight, where this angle right here is just the angle of our arc. And then this distance from here to here is the deflection away from point C. So we've got a curved section where our two materials are expanding at different rates. So they're fighting against each other and it produces the curvature. And then we've got another region that just has pure linear expansion. So that's what I'm attempting to draw with my shitty picture. Okay. So up here, just drawing my radii and all of that kind of stuff. And there's my angle theta. All right, so let's see if we can figure out what some of these things are. Hopefully, we've got enough information here to figure this sort of stuff out. So the first thing that I probably want to find is my radius of curvature, right? Well, I'm going to go ahead and I'm not going to write down all of those things because we have that expression up here. We know what all of these parameters are, so I'm not going to bother to write all of that down again. But based on that particular equation, we would wind up finding that 1 over the radius of curvature, comes out to be 260.9 inverse meters. And from this, we would find that our radius of curvature is just 3.83 millimeters. Now, this is a micro scale thing, right? We have a beam length of 100 micron for one section, 200 microns for the other section. So it might seem like that radius of curvature is excessively large. But remember that we're just dealing with an arc length along that circle. So I don't know how many of you guys are guitar nerds or anything like I am, but the fretboard of an electric guitar, ballpark, how wide do you think that is? Usually somewhere in the ballpark of 1.75 inches to 2 inches, and it actually usually changes along the length of the fretboard. It gets wider when you get to the higher frets and all that kind of stuff. But anyway, the radius of curvature of a guitar fretboard can be anywhere from 9 inches if you have a Gibson, all the way out to like 24 inches if you have a Jackson made for heavy metal. So effectively, that's just that radius of curvature is just telling you kind of how flat something is. So the larger that radius is, the flatter the surface is. So this is a very exaggerated picture, okay? So realistically, we probably won't see a huge amount of deflection or anything like that. This radius of curvature is just telling us how flat in general our overall thing is going to look. Okay, so from here, I just wanted to bring that to your attention because it might seem odd seeing something millimeter scale when we're dealing with a microstructure. So our angle is then our length from A to B. So that's literally just L1 essentially over R. And so that comes out to be, put in the numbers here, 100 microns over 3.83 millimeters is 0.026 radians or 1.496 degrees. So from those two pieces of information, we should be able to determine the deflection of our beam along the span from A to B just using this guy right here, right? So that quantity dB is going to be R minus R cosine theta, and that comes out to be 1.305 microns. And then our deflection for part C, and I legitimately think I actually have a little bit of an error in here. So let's talk about that here in just a second. So I have it written down as the deflection to point B plus L2 minus L1 sine theta, okay? So just to be clear here, let's kind of spell this out. That is this guy right here is the dB. So that's where that part comes from. Now we have an L2 minus L1 sine theta. So the L2 minus L1 is this length right here, right? And then the sine theta is giving us that portion. So why is this slightly off? Like, or why do I think I made a mistake when I taught this class 2 or 3 years ago?
Are those data?
Right. So that's that part from B to C should also change in length as well. So realistically, I think I should have this as a 1 plus alpha 2, which material is the long one? Yep. Alpha 2 times delta T as well. So it should expand slightly. So let me get out my calculator since I have to do new math because I think I made a mistake the first time I did it several years ago, right? So, goodness gracious, let's just throw in the numbers here. So 1.305 microns plus, so this guy right here is 100 microns. Then I'm going to have sine of 1.496 degrees. And then I'm going to have 1 plus, so let's see, 3 parts per million is 3 times 10 to the minus 6. Per degree Celsius times 20 degrees Celsius. So realistically, yeah, that's not going to change that much. So let's see, 100 times the sine of 1.496 times 1 plus 3 times 10 to the minus 6 times 20. X is in plus instead of times. 2.6, so this whole thing right here is 2.6108 microns. And so when we add those guys together, I wound up getting 3.9158. So let's call it 3.916 microns, which actually agrees with my original answer. Because since that temperature, goodness gracious, coefficient of thermal expansion was so small and the temperature change was also fairly small. It didn't really add that much length, but I would rather be correct without making an assumptions than correct with making assumptions. So anyway, all right, so that's really all that I wanted to cover for today. So I understand that we have a long weekend. It is my goal this weekend to get all of the missing videos, including today's video, up on YouTube and also Canvas. And then I also want to hit you guys with a homework assignment on electrostatic or capacitive sensing for sure. Probably a joint one for piezo-resistive and piezoelectric sensing. I may not give you any problems associated with this particular material. And then that should be the bulk of what's on exam 1. So I'll also try to put up a little study guide for the type of theory questions that I might give you. I still think that we are going to not get around to having our exam until that last week of January so that you guys have plenty of time to work through the homework assignments, synthesize everything before I test you on it. Does that seem fair? Okay, so that's my plan. Yes, ma'am. So I want to do things fairly differently than how I did it the last time I taught this class. So the last time I taught this class, this won't take long, I'm just making myself comfortable. So the last time I taught this class, the in-class portion of the exam was only theory questions, no calculations or anything like that. And the take-home portion of the exam was one large problem that integrated multiple things. I'm going to be changing away from that modality fairly significantly. So there's going to be a small number of theoretical or conceptual questions on your in-class test that you won't have any notes for or anything like that, but I am going to give you a list of things that I might ask you so that you can kind of prepare for it, okay? I'm also going to give you some smaller calculation style problems as part of your in-class portion. On the take-home portion, I'm probably going to give you a handful of more difficult calculation problems, and then probably one large problem that kind of ties things together. And the reason why I specifically want to give you one of those large problem that ties things together is because when you guys go, for those of you that are in MSE 502 or and are in the PhD program, when you go take your qualifier test, it will be one of those style problems that I put on that exam. So I want to make sure that you have exposure to it. So I don't really have anything already created that would satisfy that other than the big ugly problem. So I can give you an example of one of those, but that's literally all I can give you for right now. So. And I need to make some sort of difference between the graduate version of this class and the undergraduate version of this class on the exam as well. I haven't decided what that might be, but maybe the grad students will have to answer like one more theoretical question or something like that. It won't be a huge difference in difficulty because I don't have the time or energy. So. All right, you guys enjoy the long weekend. Stay safe, stay warm. I will see you on Wednesday, weather permitting.